So today's lecture will be about MIPS, arithmetic, and logic instructions. But before I start my lecture, okay, I do have a presentation about, I have a PowerPoint presentation about data representation, which is shown here. So I'm not going to go over this presentation because we already have covered these topics in the COE 202 course. But as a review, you can go back and study this PowerPoint presentation. It talks about positional number systems, binary and hexadecimal numbers, how we can do conversions between different bases, the integer storage sizes, binary and hexadecimal addition, the two's complement notation, okay, the signed integers, how we represent signed integers, and the two's complement notation, sign extension, binary and hexadecimal subtraction, carry versus overflow, and character representation. Of course, this is basically the coding of characters. But what's interesting is this sign extension here. And of course, you have to understand really the difference between carry and overflow and the two's complement notation. So let me talk briefly here about the sign extension. So before that, let me talk about the integer storage sizes. So in the MIPS architecture, a byte is defined to be 8 bits. Okay, can you see my lecture? Is it clear? Everything is clear?
Yeah.
Yes.
Okay.
Yes.
Okay, good. So the byte is shown here as 8 bits. The word is defined to be 32 bits. So 32 bits means 4 bytes. This is the word size. And in the MIPS 32-bit architecture that we are going to study in this course, all the registers are 32 bits. So when we store an integer inside a register, it's a word. We can also store it as a word in memory, 4 bytes in memory. Half word means 16 bits, and double word means 64 bits. Now, double word can be used for long integers, 64-bit integers. We can also have 64-bit integers if you would like to store them in memory. In the 64-bit architecture, each register will be 64-bit. But in the 32-bit architecture, each register is only 32 bits. So if you would like to store a 64-bit double word, you need a pair of registers. For example, if you are dealing with floating point numbers, you can have double precision floating point numbers, which are double words. It means that it will occupy 64 bits, and it requires a pair of registers to store a 64-bit number. So 64 bits means 8 bytes. Now, depending on the storage type, you can define what is the unsigned range. I'm showing here the unsigned range, but you can also define the signed range if you are dealing with signed integers. So notice how the range is going to grow exponentially depending on the number of bits. So it is from 0 to 2 to the power, depending on the number of 8s, 2 to the power 8 minus 1, 2 to the power 16 minus 1 is 65,535. I forgot to mention that 2 to the power 8 minus 1 is 255, and so on. So 2 to the power 32 minus 1 becomes more than 4 billion. And 2 to the power 64 minus 1 is this huge number here, okay? So you can see it's actually 18 and more than, we have here 18 zeros. So this is really a huge number. It's like 18 billion. So these are the storage sizes which are defined, okay, in the MIPS architecture. Type. So this is one topic that I wanted to mention. So as I said, you can go over this presentation and you can go back and understand the meaning of the two's complement representation, which is shown in this slide, but I'm not going to go over it. Already we have covered this topic in the COE 202 course. But what's interesting is sign extension. So I just wanted to mention sign extension. So suppose I would like to extend a byte, okay, that consists of 8 bits into 16 bits. Now, if this byte is signed, okay, you can use it to store a positive value or a negative value. You look at the sign bit. So if the sign bit is 1, okay, then you have to extend it according to the sign bit. So we call this sign extension. If the sign bit is 0, you extend it with zeros. If the sign bit is 1, you extend it with ones. Now, sign extension does not change the value of a signed integer. So if it is in 8 bits, it is negative 77. And when you do sign extension, you extend it to 16 bits, it is still negative 77. So the decimal value of the signed integer does not change if you do sign extension. Okay, so this works whether the number is negative or whether the number is positive. In both cases, the signed value does not change. Okay, so plus 98 is represented in 8 bits, using 8 bits as 0, 1, 1, 0, 0, 0, 1, 0. And if you would like to extend it, you have to extend it according to the sign bit. So these will be 8 zeros. This is known as sign extension. Now you can imagine that there is an infinite number of zeros appearing to the left of a positive number. And you can imagine that you have an infinite number of ones appearing to the left of a negative integer. So this is the meaning of sign extension. So you can extend it to 16 bits, to 32 bits, or to 64 bits. It does not really matter how many bits you would like to use, okay, to represent your integer. So this is a very important concept, which is called sign extension. On the other hand, if the integer is unsigned, it means it can never be negative, then we always use zero extension. But in the case of signed integers that are represented in the 2's complement representation, we extend according to the sign bit. Okay? Is this clear? You have questions about this concept? This is called sign extension because we are going to use it later. Okay, when we implement the architecture, when we go into the design of the data path, okay, and control. So I will show you that sign extension is very important when one would like to extend signed integers. Okay.
Doctor, just to refresh, how did we represent the positive in 2's complement representation?
Okay, so in the case of the 2's complement representation, maybe I need to talk about it here. Okay, so in the case of the 2's complement representation, you can start with a value. I'm showing it here for 8 bits, but really we are representing integers with 32 bits typically. In the case of the MIPS architecture, an integer is typically 4 bytes, which is 32 bits. But for simplicity, I'm explaining it for 8 bits. So you can specify whatever is the storage size, whatever number of bits. So here we start with the value, let us say plus 36. This is how we represent plus 36, okay? So this is 4, and this is 32. So if you add 32 plus 4, this will give you 36. Now, you know it's positive by just checking the most significant bit. But this is not signed magnitude. It is just a signed integer, which turns out to be positive. So by just examining the most significant bit, which is the signed bit of the number, you can tell if the number is positive or negative. So that's plus 36. If you would like to obtain the 2's complement of plus 36, what you have to do is that you have to reverse the bits. You have to obtain the 1's complement. So every 0 becomes a 1, every 1 becomes a 0, okay? So zeros become 1's, 1's become 0's, and this is the 1's complement. But you have to add plus 1 to obtain the 2's complement. So when you add plus 1, 1 plus 1 is a 0, there is a carry. The carry plus 1 is a 0, and the carry, this carry plus 0 is a 1, and the remaining bits will be unchanged. Okay, so this is the representation of negative 36. You can tell it's negative 36 because the sign bit is 1, it's a negative number. But this is not the magnitude, it's not sign magnitude representation. This is how we obtain the 2's complement. If you start with negative 36 and you take the 2's complement of it, you will get back to plus 36. So if you start with a positive number and you take the 2's complement of the positive number, you get the negative representation, okay, of the number. If you start with negative and you take the 2's complement, you get the positive value, okay, you get the positive 36 in this example. So that's the meaning of, this is how we form the 2's complement. Okay, it's the 1's complement plus 1. There is a quick way to actually obtain the 2's complement. So what you have to do is that look at the binary value, okay, and skip the least significant zeros until you encounter the least significant one. So in this example, it's plus 36. This is the least significant one. So the zeros that appear, the least significant zeros and the least significant one will be unchanged. And all you need to do is that to complement all the bits that appear to the left of the least significant one. So if you do it like this by hand, you can obtain it very quickly. So keep the 0, 0, 1 that appear on the right. So these are the least significant 2 zeros until you encounter the least significant one. Keep it 1 and take the complement of all the bits that appear to the left of this one. And this will be negative 36. The same thing, if you would like to take the 2's complement of negative 36, okay, then keep the least significant 2 zeros without any change. Keep this one, this is the least significant one, and complement all of these bits that appear to the left of this one, and you get back to plus 30. Okay? So the 2's complement of plus 36 will give you negative 36. The 2's complement of negative 36 will give you plus 36. This is the meaning of the 2's complement. Okay? Now, the 2's complement of 0 is just 0. This is the nice thing about the 2's complement, is that there is only one representation for 0. So if you take the 2's complement of 0, 0 does not really have any 1. So the 2's complement of 0 is just 0. Okay, that's the 2's complement of 0. You can read more about this, okay, which is explained here in these slides. I don't really want to spend time on this. Okay, maybe this table is important. Okay, if you would like to obtain the decimal value of a 2's complement number directly from the representation. Okay, so look how many bits exist in this number. Here I'm showing 8 bits. Okay, let us take a look at this example. So the weights are similar to the weights that exist in any unsigned integer. So the least significant bit will have a weight of 1, then you have 2, then 4, then 8. So this is like 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. Okay, until you reach the most significant bit. Now, the most significant bit here has a weight which is negative, which is negative 128. Okay, so if the most significant bit here, let me use my pen tool, if the most significant bit is 1, it indicates that the number is negative. Now, if you would like to get the decimal value, you would like to convert it from binary to decimal, and this is a signed integer. And the 2's complement representation, what you have to do is that you have to add negative 128, which is the weight of the signed bit. So the weight of the signed bit is negative. Only the weight of the signed bit is negative. Then you add plus 32, plus 16, plus 4. This will give you negative 76. So this is the decimal value of this number, which is shown on top. Is this clear? This is how we obtain the decimal value of a number which is in the 2's complement representation. So everything is the same except, okay, the weight of the signed bit. The weight of the signed bit is negative. Okay, so look here at this number here. Okay, so for positive numbers, okay, so the unsigned value and the signed value have exactly the same, are exactly the same. So if you look here at an 8-bit binary value, okay, you can say what's the unsigned value of this binary number. So if this number is unsigned, an unsigned integer, you can go from 0 to 127, and then you can continue from 128 to 255. This is an 8-bit unsigned integer. But if you look at it as an 8-bit signed integer, you go from 0 to plus 127. Okay, anything above this line is positive, which has exactly an identical value as the unsigned. So basically the signed and the unsigned value are identical, okay, above this line. And anything below this line will become negative. Notice that this will be negative 128, because the most significant bit here has a weight which is negative 128. And all of these are zero, so this will be negative 128. And if you look at this number, this is just negative 1. Because if you add here negative 128, and all of these bits will make plus 127, okay, as we have seen above here. So minus 128 plus 127 will give you minus 1. Okay? So this is how you can obtain the decimal value of a signed integer, which is represented in the 2's complement. Okay, it's in the 2's complement representation. Is this clear?
Yes. Do we assume that it is always 8-bit binary value?
No. It can be actually 32 bits. I'm going to show you in a minute. Okay, so when you are dealing with the MIPS architecture, we are dealing with 32-bit registers, and each register can store a 32-bit integer, not just 8 bits. Okay. Now, in memory, when you are storing the bits in memory, you can choose to store them as 8 bits, 16 bits, 32 bits, or even 64 bits. You can choose the size of the integer. But once it is loaded into a register, it becomes 32 bits. Okay? You can use a pair of registers to store actually 64-bit quantity if you would like to have long integers. But for the normal integer, okay, it will be just 32 bits. Okay. Any more questions? Right. Let me stop this presentation. I need to talk about. Okay. So I'm going to stop this presentation. And so go back over this presentation. It's important to refresh your memory. Okay, today I would like to talk about a new topic, which is about MIPS arithmetic and logic instructions. Okay, so this is my topic for today. So there are different categories of instructions. Okay, we have integer arithmetic, and this will be our focus in this presentation. So we have the arithmetic, logic, and shift instructions. So we have a group of instructions which are called integer arithmetic. We have data transfer. These data transfer instructions are going to transfer data between the memory and between registers. So these are called data movement instructions. We can also move data between registers if you want to, but really mainly we are accessing the memory. We have jump and the branch. These are called the flow control instructions. So we can use them to change the sequential execution of instructions. So these are going to alter this sequential sequence. So typically instructions are executed sequentially in memory until we encounter a jump or a branch. Now the branch is called conditional. It may or may not be taken. I'll talk about these in great details later, and we'll see how we can use these instructions to implement let us say if statements and loops, and also we need instructions to implement function call and function return. So these are the control instructions. We also have floating point arithmetic instructions, which are different from the integer arithmetic. They are also arithmetic, but they operate on floating point numbers and floating point registers. So it's a different group of instructions. And there are miscellaneous instructions, like we have seen the system call instruction. Okay, so the system call instruction is essential as an interface between the application program and the operating system. So it is needed to obtain a service from the operating system. Plus, we also have some memory management instructions and instructions to transfer control, okay, to an exception handler or to return from an exception. So these are like miscellaneous instructions, okay? So these are the different instruction categories that exist under the MIPS architecture. As I said, our focus in this lecture will be on the first category, which is the integer arithmetic. If you have any question, please feel free to interrupt me at any point. Or you can raise your hand, I will see that. Okay, so let us start with the R-type instruction format. So we need to define arithmetic instructions. So the arithmetic instructions, we have two different types. We have the register type and we have the immediate type. So I'll talk about the immediate type later, but let me start first with the register type. So here R means register. So it has an opcode. So this opcode occupies the upper 6 bits of the instruction. I'm going to use my highlighter here. Okay, so that's here my opcode. Okay, 6 here indicates that the opcode field is 6 bits. Now, because the opcode is 6 bits, you can define 2 to the power 6, which is equal to 64 opcodes. Now, 64 opcodes, okay, is not really sufficient to define all the instructions in the MIPS architecture. So the MIPS architecture defines more than 64 instructions. If you had only 64 instructions or less, then the 6-bit opcode field is sufficient. But because we have more instructions, the MIPS architecture, okay, defines a 6-bit function code. So for the same opcode, you can define an extension to the opcode, and this is what we call the function. So with the same opcode, I can define many functions. This is how the MIPS architecture does it. So you can have, with a 6-bit function code, you can define 64 functions. 2 to the power 6, again, is equal to 64. So 64 functions can be defined for the same opcode. And typically for integer arithmetic, we use opcode equal to 0. And we define different functions for the same opcode, which is 0. So opcode 0 is a special in the MIPS architecture. So the MIPS architecture uses the opcode 0 to define many R-type instructions. Now we know the format of the instruction. It's actually the register type from the opcode. So the opcode uniquely defines the format of the instruction. So if the opcode equal to 0, we know that the instruction is of this R type or R format, if you would like. Now, notice that there are here 3 register fields, RS, RT, RD. These are called the register fields. Each one of these fields is 5 bits. So the 5 on top indicates the number of bits inside this field. So RS and RT define the first and second source operands, and RD defines the destination. So we read 2 registers, RS and RT, and we write 1, which is RD. So RD means destination. There is also SA, which is a shift amount, which is needed specifically by shift instructions. Now notice that RS, RT, and RD are 5 bits, as I mentioned earlier. And the reason why they are 5 bits is that we can address 2 to the power 5 is equal to 32. And we have 32 registers in the MIPS architecture. And this is why we have these fields are 5 bits, because we can use a register field to address 32, 2 to the power 5. 32 registers which are numbered from 0 to 31. So these registers in the hardware are numbered from 0 to 31. We give them special names and special meaning, but in the hardware they are only 32 registers. Okay? Now, let me start by listing some instructions here. Do you have any question about the instruction format? This is important, okay, to understand, because everything is encoded using these formats. All the instructions that we are going to study, okay, are going to be encoded using the R format, the R-type format, or the immediate type format that we are going to see in a minute. Okay. Right. Let me start by listing some R-type integer add and subtract instructions. So we need to do arithmetic. Okay, so we have add, we have subtract. Okay, so these are the instructions. I'm showing them in the I'm giving examples here, like add T1, T2, T3. Now notice that T1 here is my destination. T2, T3 are my source registers. So it means that T1 becomes the value of T2 and T3. Now notice that T1 is a register which is given by name, but really it has a number inside. So this is my register convention that we have seen at the beginning of this semester in a previous presentation when I introduced the MIPS architecture. So register T1 is nothing but register number 9 because T0 is register number 8. So the meaning is that I would like to add these two registers, T2 and T3. So I have to read T2 and T3. So here our S is T2, our T is T3, and my destination is RD, which is T1. So these are the fields that appear inside the register. Now remember that T1 here is register number 9, so 9 will be encoded in binary inside the RD field. T2 here will be register 10, and T3 will be register 11. Notice that the opcode equal to 0, indicating that this instruction is an ALU R-type instruction, and the function code, okay, is shown here in hexadecimal 20 in hexadecimal, okay, for the add instruction. Okay, so that's the function code. Notice that all of these instructions have exactly the same opcode. It's the function which is different. So we have addition, which is add. We have subtract here. Okay, now both the add and the subtract are going to detect overflow. So if there is overflow, the overflow is going to cause an exception. This exception is typically going to terminate the execution of your program. Now, some exceptions might not terminate the execution of the program, but in the case of arithmetic overflow, typically is going to terminate the execution of your program. And the result will not be written to the destination register if there is an exception. So the add and the subtract, they are going to detect, okay, overflow. We also have addu and subu. These are also, okay, addition and subtraction. They are identical to add and subtract. They compute exactly the same result. However, they ignore overflow. So in the case of addu and subu, okay, they have different function codes. Notice that addu is 0x21 in hexadecimal, and subu is 0x23. So in the case of these two instructions, arithmetic overflow is ignored. So even if we have an exception, okay, even if we have, overflow, the exception will not be taken. So overflow does not cause any exception in the hardware. Yes. Yes.
You mean at you mean unsigned?
Well, yes, that's actually what the MIPS architecture defines the U. Okay, later when I see, for example, in the case of multiplication, they have multiply and they have multiply unsigned. Okay, but in the case of the main difference between add and addu is that add is going to detect overflow and cause an exception, whereas addu, okay, if there is overflow, the exception is ignored. Okay, the exception is ignored, and therefore it has no effect. This is why many programming languages, they choose addu and subu to translate the plus operator and the minus operator. So anytime you have addition, they use addu, some programming languages. And whenever you have subtraction, they use subu. Now, from the binary, from the binary addition point of view, from the hardware, addu and subu can be used to add and subtract even signed integers. So the U here does not really mean that you cannot use them, okay, to add and subtract signed integers. In fact, addu and subu, okay, can be used to compute both unsigned and signed arithmetic. So they can be used for both, because binary addition, okay, is the same regardless of whether the addition is done on signed integers or unsigned integers. If you'd like to add signed or unsigned, in both cases, okay, you can use addu. Okay, the same thing for subtraction. So the only difference between add and addu is whether you care about overflow or you don't care about overflow. So if you would like to ignore overflow, use addu. If you would like to detect overflow, use the add instruction. Okay, the add and of course the subtract. Yes, Hassan. Yes, Hassan. Okay, you have your hand raised. Right.
Yes. Doctor, first.
Yes, Fadlan.
The first question: we can we handle this exception of add and subtract, and also for the addu and subu, we will not get exception, but we will get wrong answer, right?
Yes, exactly. So basically, in the case of overflow, okay, this can happen if you are adding, let us say, two large integers, okay, and the sum is out of range. So it exceeds the maximum that can be represented, the maximum positive integer that can be represented. So you get the sum to be negative. You can notice this if you are doing programming in a high-level programming language and you are adding two large positive integers and the sum turns out to be negative. You can say, okay, how come the sum of two positive integers is negative? It has to be positive. I'm adding two positive integers. So this is an indication that you got overflow, okay? So you can choose to ignore overflow, okay? But you can see that your result is wrong, okay? That will be very clear in the case of addition. The same thing in the case of subtraction, okay? Now, how to handle exceptions? You have to write exception handlers. This is a different story, okay, which probably are going to see it also in the lab. How do we write exception handlers, okay, and how the exception will be handled? That's a different topic, okay? So typically in the case of overflow, if there is an exception, the exception handler will be executed, and many exception handlers, what they will do is that if nothing can be done, they will simply terminate the execution of the program and indicate, write a message that there is overflow, okay, and program terminated. That's if you would like to detect the overflow and terminate the execution of the program in the case of overflow. So here the programmer will be forced to go and deal with that case, okay, and write extra code, maybe use actually a longer integer, okay, so that you can actually store a wider range of values because, okay, the integer is out of range. So maybe you need actually more bits to store the result. That's how you need to handle it. Okay? Fine. So this is the meaning of add and subtract, addu, subu. Okay, they do exactly the same computation. So if there is no overflow, add and addu will compute exactly the same binary result. Sub and subu will compute exactly the same result. The only difference, whether overflow, okay, should be coded by the hardware or should be ignored. That's the only difference. Okay, so so this will take me to this. This is actually a copy from my slide from the previous presentation about range, carry, borrow, and overflow. So the bits in the hardware have no meaning. So the software, okay, it is us as programmers, we give meaning to these bits. So the hardware does not really care what are these bits. Bits are bits, okay, inside the hardware. The software, on the other hand, will give meaning to these bits. So the software can treat the bits to be signed or unsigned. So if you have an unsigned integer, you can start with a minimum, which is 0, and you go to a maximum, which is 2 to the power n minus 1, where n is the number of bits that are stored inside the register. Yani, for example, if we are using 32-bit registers, okay, then in this case, we will have 2 to the power 32 minus 1. This will be more than 4 billion. Okay, the value will be very large, 4 billion something. So you have 4 and 9 digits. That will be the maximum unsigned integer that can be represented using n bits. On the other hand, if you are storing, let us say, a byte inside a memory and you are using only 8 bits, then the maximum will be 2 to the power 8 minus 1, which is 255. So if you get a number that exceeds the maximum, and if you are adding here, let us say 2 unsigned integers somewhere here, and you exceed the maximum, then you will get a carry. So the carry indicates that your unsigned sum is out of range. That's the meaning of a carry. So you get a carry in the case of addition. In the case of subtraction, you might get a borrow. That's, for example, if I'm calculating A minus B, and A and B are unsigned, and A has a smaller value than B. So when you subtract, the result should be negative, but you cannot really represent a negative if you are using unsigned integers. So that's the meaning of a borrow, okay? In the case of subtraction. In the case of signed integers, you have the range, the 0 is in the middle, okay? And you have a maximum and you have a minimum. So the minimum is negative and the maximum is positive, okay? So if you are using n bits, okay, the minimum will be negative 2 to the power n minus 1. And in the case of the maximum, it's 2 to the power n minus 1 minus 1. Now, for simplicity, if you are using only 8 bits, okay, then n minus 1 will be 7. And the minimum will be negative 128. The maximum will be plus 127. Okay, so this is what I call the range. This is what is known as the range that can be represented with n bits. If you are using 32 bits, then the range will be much wider. You can go from minus 2 to the power 31 is negative 2 billion something. Okay, so it will have like 2 followed by 9 digits. And then the maximum will be also 2 billion something. Okay. Now, if you are adding 2 large positive integers, okay, so let me just say that I'm going to draw here. Okay, I'm going to use my pen tool. Okay, so suppose I would like to add these 2 large positive integers. This is one of them here and another one here. And I get the sum is greater than the maximum that can be represented. So this is the maximum. If the sum is greater than the maximum, we call it overflow, but overflow in the positive direction. On the other hand, if I am adding 2 negative integers, suppose that I have them here somewhere, and my sum is even more negative, so we get actually an overflow in the negative direction, indicating that the sum or the number that we are obtaining as a result of this operation is less than the minimum negative integer that can be represented. That's the indication that of overflow. So we can actually get overflow in the positive direction, or we can get overflow in the negative direction. I hope this is clear. Okay. So this is the meaning of overflow. So as we have seen, carry is useful when you are dealing with unsigned integers. So we use the carry here. Okay, whether you are adding or even subtracting, we can check the carry. And it indicates that the unsigned sum is out of range. Overflow is useful when adding or subtracting signed integers. And it indicates that the sum is also out of range. Either it's greater than the maximum positive or it's smaller than the minimum negative. That's the meaning of overflow. So we can actually get overflow in 2 directions. That's the meaning of overflow. Okay, so the range here is specified for 32-bit integers. Notice that for 32 bits, it's 2 to the power from 0. For unsigned, it's 2 to the power 32 minus 1. In the case of signed integers, so here n minus 1 will be, okay, negative 2 to the power 31. Here 2 to the power 31 minus 1. Okay, because it's n minus 1. Okay, here's an example about, this is one example about there is a carry, but there is no overflow. So the first number is negative. Okay, you can obtain its decimal value. It has probably a large decimal value. The second number is negative. You can see that actually from the most significant bit. So the weight of this bit will have a weight of negative 2 to the power 31. And all the remaining bits will have a positive weight. Now, this is at position 31. So this is why the weight is negative 2 to the power 31. This will be, for example, plus 2 to the power 30, plus 2 to the power 29, and so on. Of course, these are large weights, but this is what you need to do, is that you have to add their weights to obtain the decimal value. So if you add this negative plus this negative, notice 1 plus 1 equal to 0 and the carry. Now this is the carry, which is shown here. 1 plus 0 is equal to a 1 without any carry. Here I have 1 plus 1. If you add these two ones, which are shown here, okay, you get a 0 and you get the carry. You add 3 ones, you get a 1 and there is a carry. 3 ones, 1 and the carry. Okay, 1 plus 0, there is a 1, but there is no carry, and so on. You can continue like this all the way to the end. So notice at the end, I'm going to get this carry. This is my final carry. Now, this carry cannot be stored inside the register. Why? Because the register is only 32 bits. So when the hardware does this addition in binary, it's going to produce a 32-bit result. And the final carry here is ignored, or it is discarded, okay? So the carry cannot be stored inside the register because the register is only 32 bits. Now the question is there a carry? Yes, definitely there is a carry, okay? You can see that clearly when you add these two numbers in binary, but is there overflow? The answer is no, there is no overflow. Notice that the last two carries, this carry and this one, okay? So these are two carries, they are identical. And because they are identical, then there is no overflow. So there is no overflow. So if you look at this number here as signed, then this is the correct signed result. So when you are adding these two numbers, we are getting exactly, so we are getting the correct result, okay? So if you look at them as unsigned, then the result is out of range. But if you look at them as being signed in the 2's complement representation, then the sum is within range and there is no overflow. So in this example, we have a carry, but there is no overflow. Okay, so the sum, okay, is correct if you look at these numbers to be signed. So if you are adding signed integers, then the sum is correct. If you are adding unsigned integers, then the sum is out of range because we got the carry. So there is a carry, but there is no overflow. Here's the second example. I don't have a carry, but there is overflow. Now look at the first number here. It is positive, and the second number is also positive. You can convert them from binary to decimal, but I will not do that. Whatever are their values, we can just actually add them in binary. At the end here, when I'm actually adding them, notice that 1 plus 1 here, okay, notice that this one plus this one, okay, let me just highlight them, okay, is equal to 0 plus a carry. So we got a 0 and the carry. 1 plus 0 plus 1, 0 and the carry. 1 plus 0 plus 1, 0 and the carry. So the carry is going to propagate all the way here to the most significant bit, okay? Now this 1 plus 0 is equal to a 1, but there is no carry. So the final carry here, this is my final carry, is 0. So the carry is equal to 0. Is it overflow? Yes. Why? Because the last two carries are different. And if the last two carries are different, this is an indication of overflow. So the hardware can easily detect if there is overflow or no overflow by comparing the most significant, okay, the last two carries, the carry on the most significant bit and the final output carry. So there is no final output carry, but the carry on the most significant bit is 1. So when you XOR these two bits, you get a 1, and this is an indication of overflow. You can also detect overflow very easily as a programmer. Okay, you are actually adding two positive integers, and the sum is negative. How come the sum of two positive integers is negative? That's an indication of overflow. Okay, that's the meaning of overflow. Okay, is this clear?
Yes.
Do you have any question about this?
Doctor?
Yes.
Yeah, how can we deal with overflow here?
Well, as I said, it means that the number cannot be represented in 32 bits. If I had one extra bit, okay, here, then this bit should be 0. Okay, and if I had one extra bit here, if I had 33 bits, okay, 33 bits in my register, I only have 32 bits inside my register because my register is fixed in the hardware. But if I had one extra bit, okay, in the hardware, then this bit should be 0, indicating that the number actually is positive. But because I have only 32 bits, I have to stop here. And the most significant bit 1, indicating that the number is negative in the 2's complement representation. This is the sign of overflow. I'm adding 2 positive integers and the sum is negative. Okay? So if you look at the number here to be unsigned, it is correct because we did not really get a carry. Okay, and if you look at it as unsigned, it's fine. There is no problem. It's within range. But if you look at it to be signed, in the 2's complement representation, the sum is negative. It should not be negative. It should be positive. So if I had one extra bit, then it will actually, if I had one extra bit inside my register, then this bit would be 0, and it means that the number becomes positive. Okay, so the indication of overflow, it means that the sum is out of range when you look at the sum as a signed integer. That's what it means. Okay, is it clear now? So how do you handle overflow? One way to handle overflow is to allocate more bits. Okay, so if the number, if 32 bits are not really sufficient, okay, you need to allocate more bits in memory. You can use an additional register. Okay, you can actually take this carry and propagate it. Okay, but this will complicate programming. If you just would like to do it with one add instruction, it's going to generate overflow because the sum cannot, the signed result cannot fit in 32-bit register. Here's another example. Okay, a third example. Let me just stop here because I'm running out of time. In this example, clearly you can see that we have a carry and we have overflow. Notice that 1 plus 1 here is a 0, and there is a final carry. Notice that there is no carry here. This is 0 here. There is no carry. Okay, so 0 plus 0 equal to 0. There is no carry. So here, basically, you can have like a 0 on top. So these actually, the carry on the most significant bit is 0, which is different from the last final carry. So because the last 2 carries are different, this is an indication of overflow. You are adding a negative to a negative, and the sum is positive. It cannot be positive. It has to be negative. Okay, so this is an indication of overflow. And because we are getting a carry here, if you look at these 2 numbers to be unsigned, it's also the unsigned sum is out of range. So both the unsigned and the signed sums are both out of range in this example. Okay. Okay, so that's it for today. I talked about basically arithmetic, okay, and the difference between carry and overflow in great detail. Okay, so next time I will be talking about other instructions, the logic instructions and or XOR. Okay, there is also NOR. I will talk about shift instructions. I'll talk about pseudo instructions. All of these are really important concepts, okay, important instructions that exist in the MIPS architecture. Okay. I would like to continue on my last lecture. I talked about addition and subtraction, the add and subtract instructions. I talked about overflow, the meaning of overflow, and how overflow is different from the meaning of carry. Let us see how we can use these instructions in the programs. So suppose I would like to translate, okay, the f becomes g plus h minus I plus j. So these are variables that you are using in your program. And if you are programming in assembly, you have to allocate registers for these variables. So if you are programming in a high-level programming language, typically the compiler does the allocation of registers for the variables. But since we are programming directly in assembly, then this is done directly by the programmer. So we need 5 registers because we have 5 variables here. So I'm going to use here the temporary registers from T0 to T4. So remember that T0 is register number 8 in the register set. So T0, I'm going to use T0 for F, T1 for G, and so on, and T4 for J. So these are called the temporary register, and remember that T0 is register number 8, T1 is register number 9, and so on. So how do we translate this? Okay, so how do we translate this expression? Okay, anyone can suggest the answer? It's very simple, very easy, right?
We can create a register that stores the value of G plus H, and
yes.
Another register for I plus J.
Yes.
And then subtract the two registers.
Okay. Okay. So we can actually store the result of, so we need an add U instruction. We can use add or we can use add U. The difference is that whether we care about overflow or we want to ignore overflow. So the add is going to catch overflow, it's going to cause an exception in the case of an overflow. But if I would like to ignore overflow, I can use the add U instruction. So we have to add T1 plus T2 because these contain the values of G plus H. Put the result in a temporary register, let us say T5. Then another add U to calculate I plus J. Okay, so the first add is going to calculate G plus H. The second one is going to calculate I plus J. So we're going to add T3 plus T4, put the result in another temporary register, for example, T6, and then we can subtract. Okay, so subtract T5 minus T6 and put the result, final result will be in T0. And T0 is nothing but the register that we are using for the variable f. Okay. So two add instructions, one subtract, and this is the translation of the above expression. Notice that I'm using here add U and sub U because I would like to ignore overflow. Now you can say that this is how we write the instructions in assembly. Now the assembler is going to translate these instructions into their binary representation. So these are of the R format, and when we take these instructions and we translate into binary code, for example, take the first one, then the opcode will be equal to 0. Okay, the opcode equal to 0, indicating that this is an R format instruction. And the function code is this number here. Okay, so it is this number in binary, indicating that this is an add U instruction. We can have different function codes for add U, subtract, and sub U. They have different function codes. And we have the first source register here is T1. So T1 is register number 9. So we write 9 in binary. T2 is register number 10. So we write 10 in binary. And the destination, which is register RD, is register T5, which is 13 in binary. Okay, so this is register number 13 in the hardware. And there is no shift amount. The shift amount is just 0. So this is how the instruction will look like in binary. And this is how it is stored inside the memory of a computer system. The entire instruction is 32 bits, is divided into many fields. We have a field for the opcode. Okay, the opcode here indicates that it's an R type or an R format instruction. Do you have any question about this? Is this clear? So this actually shows how the instructions are represented in binary and how they are translated by the assembler. Right, let's move on. Okay, there are, in addition to the addition and subtraction, we have the logic instructions, bitwise instructions. So we have 4 of these. We have AND, OR, XOR, and NOR. Yes.
If we are using ADDU,
yes,
then what will the result in the register will look like, or add? Sorry.
It's the same as ADDU. Add and ADDU produce exactly the same result. So this is the instruction. Okay, so what we have here is the instruction in binary, but when this instruction is executed by the hardware at runtime, At runtime, the CPU is going to fetch and execute this instruction. So this is done at runtime. The assembler only translates. Okay, it's translated. It translates the instruction from assembly to its binary representation, but it does not execute. So the assembler does not execute. The hardware, the CPU, executes these instructions. And when the CPU executes, then the addition will be done. The difference between add and addu is that, well, let me say that they are similar because they produce exactly the same result in the hardware. The only difference is that in the case of overflow, add is going to cause an exception, whereas addu is going to ignore the exception. But both of them are going to do exactly the same computation in binary. So the ALU is designed to execute the binary instruction. Okay?
Okay, clear.
Right. So here I have the logic bitwise instructions. So we have AND, we have OR, we have XOR, and we have NOR. Okay, these are 4 logic instructions. Their meaning is shown in the second column. Okay, so AND is called a bitwise AND because we do the ending of the bits. So we are ending the bits of T2. We have 32 bits in register T2 and 32 bits in register T3. And when we do the ending, we produce a result. This result is written into register T1. OR is also a bitwise OR because we are doing the ORing of the bits. We have XOR and we have NOR, which is not OR. So these are instructions. These are instructions that exist in the instruction set, and you can use them in programming. Now, the opcode equal to 0, because all of these are of the R format, and each one has a unique function code. So you can see that the function codes are different for each one of these instructions. RS in this example is register T2. Okay, in all of these examples, this is RS, this is the first source register. RT is my second source register, it's T3. And RD is my destination, where we would like to write the result, it's T1. Now notice that in assembly, we write T1 before T2 and T3, whereas T1 appears in the RD field inside the instruction after T2 and T3. So the binary representation or the format of the instruction does not correspond to the syntax of the instruction, which is written in assembly language. Now the meaning of AND is very simple. You get 1. Okay, so when you AND 2 bits, you have to have these 2 bits 1 and 1 to get the 1, otherwise you get a 0. In the case of ORing, you get a 1 if either 1 is a 1, either bit is a 1. Okay, you get a 1 here. Okay, in 3 cases, you get 0 if both bits are 0. In the case of XOR, it's an exclusive OR. You get 1 if exactly one of the input bits is a 1 and the other one is a 0. If both of them are 1, then the XOR will give you 0. So XOR will give you 0 if both of them are 0, 0, or both of them are 1, 1. NOR is just not OR, which is the complement of this column here. But this is just for a single bit. And each register has 32 bits, so we have to operate on these 32 bits in parallel. Okay. Notice that there is no NOT instruction. The NOT instruction does not exist. So NOT, okay, if I would like to take the complement of all the bits in T2 and put the result in T1, there is no such instruction because you can actually use the NOR instruction. So when I do the ORing of T2 plus T2 with itself, T2 or T2, you get T2. And then when you take the NOR, you get basically the complement. Okay, so you can use the NOR instruction as in NOT. Okay, so for this reason, the designers of the MIPS architecture did not use a NOT instruction because they can have the NOR instruction. And the NOR here, okay, when you take NOR T2 with itself and you write the result into T1, it's the same thing as taking the complement. So it will give you exactly the same result. Okay, is this clear? So these are called the logic bitwise instructions because they operate on the 32 bits, bitwise, bit by bit. Now, you can use these in programming. You can use the AND instruction to clear bits. So if you end with 0, you will get 0 regardless of the bit X. So if you take any bit X of a register and you end it with 0, you get 0. If you OR with 1, you get 1, okay, regardless of the bit X. So you can use the OR instruction to set the bits. The AND instruction is useful to clear the bits. You can use the XOR instruction to toggle the bits, because when you take a bit X and you XOR it with 1, you get not X. So you can use the XOR to complement the bits. Here's an example. Suppose that we have, this is T1, this is T2. I'm showing T1 and T2 in hexadecimal because it's more compact to show it in hexadecimal. Remember that each digit in hexadecimal is what? Okay, each digit in hexadecimal, 4 bits in binary. So this A, yeah, so this A will be 1010, right? The F here, for example, in T2 will be 1111, okay, in binary. Now, suppose I would like to take the end of T1 with T2 and put the result in T0. What do I get in T0? Let us end T1 and T2. Notice that I have here 8 digits in hexadecimal, means 32 bits in binary. So you see that here T1 consists of 32 bits and T2 consists of 32 bits. But using hexadecimal is more convenient, it's more compact. So what do I get as a result? Go ahead.
We'll get A.
Yes. Just
you
A?
need the A, B, C, D, then zeros.
So you get A, B, C, D, then 0, 0, 0, 0, right? Because when you end with 0, you get 0. When you end with F, you are ending with 1s. So you get exactly the same digit. Okay, so therefore you get A, B, C, D, 0, 0, 0, 0. Yes, this is the correct answer. How about when I OR T1 with T2? What do I get when I OR?
F, 1, 2, 3, 4.
Exactly, F, 1, 2, 3, 4. The answer is easy, right? Because when I OR with 1, I get 1. When I OR with F, I will get F. How about when I XOR T1 with T2? What do I get?
Zero, 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 zero. Oh no, sorry.
So basically, when I XOR with 1, I get the complement. So what's the complement of A?
5.
Yes, 5, exactly, because 5 plus A will give me 15, which is F in hexadecimal. So basically, you are going to complement the bits of A. A is 1010, so you get 0101, which is 5, yes. You can also look at it from the decimal point of view, so from the hexadecimal, sorry. In hexadecimal, if you add A plus 5, you get 15. Okay, so when you complement A, you get 5. When you complement B, what do you get?
4.
Yes.
We'll
So
get 5, 4, 3, 2.
Yes.
Uh,
Now we are XORing with zeros, right? The least
yes.
So okay, so when you XOR with 0, what do you get?
Same.
We'll get the same number.
So give me the final answer.
5, 4, 3, 2, 1, 2, 3,
Yes.
4.
Yes. Okay. So that will be the final answer in T0. So this is when you XOR, you are going to write this result in T0. This is the result that will be computed by the XOR instruction. How about NOR? I already have calculated the OR, right?
Yes.
So all what we have to do is just the complement.
Yes, which will be 0, 0, 0, 0, 0, 0, 0, 5, 4, 3, 2.
Why 5?
No. No.
What's the complement of 1?
It is D, E.
E. Then complement of 2.
E, D.
D.
Then
D.
C.
So it's E, D, then C, then
B.
yes. So this is the final answer that you will get in T0. Okay, is this clear? So this is how you can use the logic bitwise instructions. They are called bitwise because they operate on the bits. Okay, so each bit is ANDed or 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 XOR or NOR with its corresponding bit. Okay, so bit by bit, we do the logic instructions.